Hey guys, this is Arvind and you're watching Learn with Arvind. In this video, we'll be discussing what Fourier series actually is. And in the upcoming videos, we will be solving few problems on Fourier series. Let's enter the video. What is the idea behind the Fourier series? We will be adding simple periodic functions such as sines and cosines to represent a complex function, to approximate a complex function. Before going into Fourier series, let's see what periodic function means. If the value of a function repeats itself at regular intervals, this is what we mean by a periodic function. For instance, take a sine function. It repeats its value over a period of 2 pi. It suits for cosine function too. Now take a square function. If we wish to approximate a square function by using a sine, we are adding a sine wave to a square function. Now you could see clearly we've got a approximation of square wave using sine, but it's not a good approximation since a lot of area is left behind. There are a lot of leftovers. We've added a lot of unnecessary area and we've left which is within the range of square wave. Now we are adding one more sine wave. It's a good approximation compared to the last case, but it is not a good one though. Now we are adding sine waves until it reaches a point when it becomes a square wave. Now you can see that it's a good approximation of a square wave using a sine wave, but there are jump overs from square waves. This is what we mean by Gibbs phenomenon. When a function and its derivatives are continuous, then the function can be expanded using Taylor series. For both continuous and discontinuous function, we can expand a function using Fourier series. And the reason why we expand using Fourier series is it is easier to solve when a function is in sines and cosines rather than in a complex form. Fourier series of a non-sinusoidal periodic function is given by f of x is equal to a0 by 2 plus summation n is equal to 1 to infinity n cos nx plus bn sin nx, where a0, an and bn are predetermined constants. It tells us the amount of cos and amount of sin present in the Fourier series. These constants an is given by 1 by pi integral minus pi to plus pi f of x cos nx dx. For an we will be substituting 0 in the place of n and we will be getting 1 by pi integral minus pi to plus pi f of x, since cos 0 is equal to 1, f of x dx. Bn is given by 1 by pi integral minus pi to plus pi f of x sin nx dx. The Fourier series which we written here is for a range of minus pi to plus pi. If you are having any other interval other than minus pi to plus pi, in the Fourier series for the interval minus L to L, then Fourier series for the interval minus L is given by f of x is equal to a0 by 2 plus summation n is equal to 1 to infinity n cos n pi x by L plus bn sin n pi x by L. Here the constants a0, an and bn are given by an is equal to 1 by L integral minus L to plus L f of x cos n pi x divided by L dx. The same way if we substitute a0, it is given by 1 by L integral minus L to plus L f of x dx. Bn is given by 1 by L integral minus L to plus L f of x sin n pi x divided by L dx. We will be seeing derivation of a complex form of Fourier series in the next video, and we will be solving further problems in the upcoming videos. Stay tuned, it's Learn with Arvind. See you guys.